Buddy, the chairs only have one laptop between the two of us, so we definitely need someone to volunteer to take notes before we can start. If you're willing to do that, please come and talk to us. Oh, hey.
One.
Can everybody who's not here for the meeting please go out? Anybody who is here for the meeting, sit down and, act like we're having a meeting.
Test.
One more request going for someone to take notes. Thank you very much. All right, I think, is this working? Okay. Okay, so let's get started. The usual note well, which presumably you've all noted well by now. Yeah, so let's go straight to talking about document status. Right now, I guess the thing that has been keeping people the busiest in terms of moving stuff forward is problem statement, which, as quite some number of you know, got submitted to the IESG some time ago. It received, let's just say, more and more active commentary from the IESG than we had anticipated. And some of which is more straightforward to address by just doing necessary edits to the document, and some of which were kind of kind of beyond the scope of just going and editing one document. So it took us some time to figure out What to do about it? There were 4 discusses open against the document. The authors have gotten 2 out of the 4 cleared up, thank you. And I think we have agreement in principle on the necessary changes for a 3rd, and hopefully the 4th will also be taken care of by the end of the week. So it's looking promising anyway for moving the problem statement forward. Yeah. So next document is that one, the architecture. We completed the working group last call. There's a number of things that we definitely need to look at doing though before moving it into the IESG, sort of taking a lesson from the last one, including beefing up the security considerations, going and doing another, look at RFC 5706 to see what is actually going to be demanded of us for management considerations. Yeah, so a number of comments to roll back in, and depending on how much this ends up in changing the document, I guess we'll decide whether it requires another formal working group last call, or in any case, the members of the group will have the opportunity to review the changes, of course. The authors of OEM use case have asked for it to be last called. We will start that this week. And finally, we have 2 more use case documents. One of the things that came out of our last intense interaction with the IESG was, let's say, guidance that we should get requirements sent to them and stop sending them requirements before we ask them to process the architecture document. So kind of the next goal then is to focus on moving the remaining 2 use case documents along. And what we've written here is our goal is substantial progress by IETF 96. It would be awesome if that substantial progress represented a working group last call completed, but we'll do whatever we can do. We don't want to prematurely close the document, but on the other hand, we can't keep them open forever, and especially we haven't been explicitly told, I don't think, that they will definitely be blocking, but it's, I think, pretty clear that the easiest path forward would be to have these guys cleared before we ask the IESG to process the architecture document. So, anything else? No. You would think that would be a locking connector, but no. Okay, so Stefano, please. Sorry, unless there were any comments on that, but it seemed pretty non-controversial.
Hi, I'm Stefano Providi. So, as already anticipated by John, most of the activity has been focused on the problem statement draft. Is now in ISG review. We got quite a few comments and discuss. We are pretty close to have answered, cleared all of them, but not. We are close, but probably not yet there. We still have to add some text, especially regarding, I think, fast reroute and microloop avoidance. Otherwise, we added all what was requested, the security section, manageability section, explaining better explaining the applicability of segment routing over data planes, MPLS and IPv6. There was some text that was in between unclear and conflicting, comparing RSVPT-based traffic engineering with segment routing traffic engineering. So we kind of removed that text. We also put pointers to the V6 draft of segment routing, so the segment routing header draft for all the V6 instantiation of segment routing. We also defined better the applicability interdomain, putting boundaries on what by default a segment routing node is supposed to do or not to do. Same for the requirements. Most of the requirements in the original version of the draft were written with the should terminology, and so we clarified and made a more consistent description of what are the requirements that are mandatory and the ones that are just a should. And we also added some clarification text on the source routing applicability in MPLS, means essentially related to the label stack depth. We still have received, obviously, all the comments that we addressed on emails, but that didn't trigger changes in the draft itself. There is still a point here. We need more text about fast route and macroloop avoidance, because in the problem statement draft we mention traffic engineering, fast route, macroloop avoidance, but we don't give any explanation or introduction or even a context definition on this. And we agreed with the ISG reviewers that more text should be put into the resiliency use cases draft, so that the problem statement draft can point to the resiliency use case draft and move on. And so that's what we're going to do. We're going to issue a new version of the resiliency use cases. One comment was about the name Spring. So one of the comments from the ISG was Spring term should be replaced by segment routing, because segment routing is the technology that the working group is defining. So while I cannot disagree with that, we prefer to stick with the terminology that we always had in the Spring working group. So we, as long as we talk about the problem statement, we keep the Spring terminology. The use, yeah, there was a comment on the traffic engineering use case. The comment was about the lack of description of the multiple TE use cases that Spring should or should not address, or should details or not. And in fact, the question I have here is that we had one of the very first drafts submitted in Spring Working Group was the segment routing use cases draft that explained in details how traffic engineering can be addressed with segment routing. But that draft has been abandoned and expired because of the problem statement. So I'm not sure if we need, and this is probably a question for the chairs and for the whole group, do we need to resurrect that draft and document more, with way more details, how traffic engineering can be addressed with segment routing, or should we stay as we are today with a problem statement with a high level definition of traffic engineering? And so, because the comment, I mean, it's a comment, it's not a discuss, so it's not something that will block the document, but still, it's something that we probably have to answer to. There were some comments regarding the IPv6 instantiation of segment routing. Again, here I think it's just a matter of giving the right pointer. So we replied to the comments by pointing to the V6 draft of segment routing. I don't think the problem statement should go into the details. We also have a specific V6 use cases draft in Spring that describe how segment routing is applicable to V6 data plane. So I don't think problem statement draft should go more in that, more into the details of that. Same for the comments about the RH0 deprecation in V6. Everything has been described in the 6-man segment routing header draft, the deprecation of RH0, the motivation behind it, why do we use a different routing header type, how do we address security with this new routing header type, and so on, with the HMAC, and so everything is in there. And so this is also related to the security section of the segment routing v6 draft. Everything is in there. So probably what was missing in the problem statement is the right reference, the right pointer to those drafts. That's pretty much it on the on the work that has been done on the problem statement. As John said, one of the comments, I mean more than one comment that has been made on the problem statement draft is, do we need a problem statement draft for a technology which is already defined in architecture document, in protocol extensions, and it is already deployed, being implemented by multiple vendors, interoperable, and already deployed. So it's probably a bit late to come with a problem statement or requirement list, but still, I think all the authors agree that a substantial amount of work has been put on those drafts, and not only the problem statement draft, also the different use cases draft. And so we want at least to see those drafts to be published, informational or whatever, but we want those drafts to go through the whole process and not being abandoned. I mean, this is the view of the co-authors. Other drafts that we see that will also need to get to the next level are the MSDC, EPE, and the sorry, this is the wrong word, is V6 use case, IPv6 use cases. Because all those are the drafts that not only describe the use case, but also introduce the need for a protocol extension, either in BGP or BGPLS, or in the V6 data plane in the case of IPv6 use cases. So clearly, we want to move on those drafts as well, because those are the kind of companion documents with the different protocol extensions that we have for segment routing in different working groups, from BGP, ISIS, OSPF, PCE, and 6-man. And of course, there will be next in line after the problem statement. From an architecture perspective, we have the 3 drafts, the segment routing MPLS, and LDP interop. We did some work. All the comments we received so far, we still have to integrate all the comments that we received. So work is not finished there. As John said, the goal is to come to next meeting with substantial progress also on those 3 drafts that represent, I mean, the main architecture and the instantiation on a MPLS data plane. Those are the 2 drafts. I think one of the 2, the large-scale interconnect, is in the agenda for today. It was supposed to be, but I don't know if it got there. There have been little discussion on the recursive information in segment routing. This came from a requirement, I think, at least a couple of meetings ago. So we published a draft, but we got little feedback. So if you can read it and comment, that would be useful. And the large-scale interconnect, the recent update, I think the update missed the window for the submission, but I don't know if there is no slot in the agenda today. Okay, they're not presenting. But those clearly are the draft that would be interesting for the working group to evaluate for the adoption. That's pretty much it.
Any questions or comments? If not, Les, you're up next.
Okay, I'm Les Ginsberg, my esteemed co-authors. This is a bit of review. We presented version 00, the draft, at the last IETF. We have not issued an update. We're getting pretty close to doing so, but we did have some good discussion on the list, and we did make some progress. So segment routing identifiers are global in scope, and there needs to be a policy established as to what to do when conflicts occur. This issue is cross-protocol, so we're not talking about this for ISIS or OSPF, we're talking about it for segment routing as a whole, which is why we're talking about it in this group. There are essentially two issues that the draft tries to address. The first one, we had a very healthy discussion on the list, and we have achieved consensus. This was handling what happens when there's you receive an invalid sRGB set of entries. Invalid meaning that there are multiple ranges advertised and there's some overlap between at least some of the ranges. We agreed upon some new text. This is, again, we haven't issued an update, but I did publish this text as an email on the list. At least all the folks who are actively discussing this have agreed that this is acceptable. The key point is in red here. If you get overlapping ranges, then we ignore all of the sRGB advertised by that node, and we treat the node as if it didn't advertise any sRGB at all, which means for global SIDs, it has no mapping of SIDs to labels. There was also an update to the SR MPLS draft to clarify what should be done in cases where a node doesn't have a valid sRGB. And so we're now referencing the SR MPLS draft, which is defining the correct behavior. So what's left is prefix SID conflict resolution. This is a different problem than the sRGB problem because sRGBs are configured locally on a given node, and therefore the consensus was it should be possible for the node that's processing the configuration to make sure that there is no conflict. But with SID advertisements, SIDs are advertised by many nodes and possibly multiple mapping servers. So you don't have configuration confined to one node, and it is possible for conflicts to occur. This is a quick summary. Again, the version 0.0 of the draft is agnostic at the moment. It talks about a few different types of solutions, but it hasn't taken a position on exactly which one is the one we hope to achieve consensus on. There are basically two policies. One that says if you have conflicting advertisements, you ignore them all. And the other is to apply some preference rule and to say, I'll pick this one and I will use this advertisement, I won't use the other advertisement. For the ignore, I guess the advantage of ignore would be that it's easy to diagnose in the sense that you're no longer going to be using SIDs to forward traffic for those destinations. But the downside, of course, is that you're likely to be dropping a lot of traffic. For the use of the preference rule, it's when you have conflicts, it's possible that you will be able to successfully forward some portion of the traffic. The potential downside is it might be a little harder to diagnose because you may not notice at first that there's actually a problem. Maybe the conflicts are with destinations that are not actively being used or at least not noticed. So a little bit of terminology. This is talked about more explicitly in the draft, but what's a mapping entry? A mapping entry is essentially defining a prefix, a starting SID, and a range. So a couple of simple examples there. What kinds of conflicts can we have? We can have two types of conflicts. a prefix conflict where you assign different SIDs to the same prefix, or you could have a SID conflict where you assign the same SID to different prefixes. Both of these cases need to be handled. The prefix conflict is what I call intra-topology, or within the scope of a VRF, if you like, whereas a SID conflict is inter-topology, or across all VRFs, because you have one label space on a box that's shared among all of the VRF contexts that are configured on that box. How do we achieve consistency? Some key points: you must have the same database on all the nodes. If you have different databases, clearly no matter what rule you define, it's likely that two boxes will come to two different answers. Local configuration does not matter unless you actually advertise it. If I configure SID locally and I don't tell anybody else about it, I cannot use that in my conflict resolution, because if I do, I'll be using information that nobody else knows about. Priority, whatever our preference rule might be, if we decide to use one, is not based upon the source of the advertisement. That means I don't care what the router ID or the system ID of whoever advertised it. I don't care if it was configured locally or if it's configured remotely. I have to have the same view on the database on all the nodes in order to come up with the same answer. There are generally two categories of information. You get SIDs that are advertised in the prefix reachability advertisements by the routing protocols, and you may have mapping servers configured, and you will get advertisements from one or more mapping servers. Again, if you have local configuration, only what is advertised, either as SRMS entries or in prefix advertisements, can be considered as part of your database for conflict resolution. And of course, you use the advertisements that you receive, both the ones that you advertise and the ones that you get from your protocol peers. So here's a proposed preference rule. This differs from what is in version 00 of the draft. It's been revised based upon some feedback that we've already received. The key element here is the first one, which says that smaller range is preferred. That's key for two reasons. One is that it means that if you misconfigure one entry that has a range of 100 or 500 or 1,000, you will not wipe out a whole bunch of entries with a range of 1. Prefix advertisements, by definition, have a range of 1. SRMS advertisements can have whatever range is specified in the advertisement. So rule number 1 inherently biases the choice towards prefix advertisements, but not exclusively. Why not exclusively? Because you can have cases where, let's suppose you're doing an SR-LDP mixed deployment, and you're using the mapping server to advertise SIDs for the nodes that are currently not SR capable. As you start to upgrade the nodes that are that were not SR capable to become SR capable, you will introduce local configuration on those nodes for the SIDs that the prefixes that they own. That configuration is just as potentially error prone as any other type of configuration. So it's just as legitimate to think that you may want to continue to use the SRMS advertisements that you've been using prior to that node becoming SR capable. So we don't define this as a rule that says prefix advertisements are always preferred over SRMS advertisements, but it is biased that way because prefix advertisements are inherently a range of 1. The rest of the tiebreakers, the particular order in which they're done, I don't think is critical. It's just important that We cover every element of a mapping entry, so we're guaranteed to find some difference between the two if there is one. If all 5 of these things are the same, then you have 2 identical entries. Doesn't matter which one you use. So 2 easy examples here. Just illustrating, okay, smaller range wins means the 1.1.1.1 and the 2.2.2 entries are going to win, and the 3.3.3 entry, which has a range of 50, is going to lose. If you used a larger range wins, then you would wipe out the first 2 entries with the single mapping server entry of 3.3.3.3. And of course, you could have a much larger number of prefix advertisements than just the 2 I show here. So if you use this preference rule, then the question is, when you detect a conflict, what do you do? There's 3 choices that we outline on these next 2 slides. One of them is what I call quarantine. So the first column shows we have 3 advertisements. We decide, because the smaller range wins, that the first 2 elements become part of our active policy, and we take the 3rd entry in its entirety and we quarantine it. We exclude it, we don't use anything. There's a second policy, which is to simply resolve the particular entries that overlap. So again, we start out with the same 3 advertisements. The first 2 are winners because they have the smaller range. We take the 3rd entry and we start to break it into pieces, because in actual fact, the only conflicts that exist are for SID 10 and for SID 20. And so we break the first advertisement into the 3 pieces that have non-conflicting ranges, 1 through 9, 11 through 20, and then 21 through 30. And I guess that should have been 21 through 50, but oh well. Yeah, well, that's what happens when you do your slides late. Anyways, you get the idea. The portions of the range that are in conflict from that entry with a range of 50 are then excluded. The 3rd policy is to say, well, I don't know which one of these entries is the correct one, and so I'll just ignore them both. And what you end up with here is all of the advertisements in this example are ignored. So I'm going to come back to this in a second, because that, I think, is the key element. But from next steps, what we want to do is to at least start to get some consensus on what our policy should be. Issue V1 of the draft, V00, is actually coming close to expiring, and hopefully we have enough consensus. We want to move this to become a working group document, and then obviously we can continue to discuss and refine. So I'm going to open this up, but to me the key point to discuss here is these choices about quarantine, overlap, or ignore, and potentially the preference rule as well.
AC Lindum, so I think this is good work to get some consensus, and I know there's a long discussion on the spring list. I have one question. If you quarantine or exclude entries, would you have the implementation be expected to bring those back if the overlap were corrected?
Yes.
You would.
In other words, every time you get an update to the database,
So
you have to rerun your algorithm, figure out what's still in
Yes.
conflict. And
So you'd keep all the
yes.
state.
When I say exclude, they're still in the database, but they're not used in terms of installing things in the forwarding plane.
Alvaro Rutana, Cisco. In the selection process, and there was a comment in the Java room about the same thing from Stuart. The selection process, show it, can you? That's step number 2. Why is IPv4 preferred over v6? That seems to be
Because-
counterintuitive, counter everything.
Because
Yeah.
4 is lower than 6. I don't care. I mean, if there's a consensus that, gee, it's a brave new world, we should prefer V6 over V4, I'm fine with it. I don't think we really care.
I think in general, that's the direction, obviously, the world is going and everyone else, so we should change that.
Sure.
I'm Justin Sir Erickson. So, well presented by Les, there've been really a lot of discussions between people who are implementing segment routing, and it's crucial that every vendor in a network implements same selection policies, otherwise you end up in a mess. So it's been discussed, and from implementation perspective, by we I mean majority of the vendors, we agreed. So would be really good to hear from service providers whether they see the operational practices coming along with this preference rule we've put together, and if it is, would be great to progress quickly. So there's no discrepancy on different vendors in the same network.
Jeff, is your primary point here that we need to hurry up and close on this so that implementers can finalize their?
Yeah, as soon as
implementation?
possible. Otherwise, you get different vendors, same network, having different preference rules, and it becomes undeployable in this case.
Yeah, John, that's a good point, because we have implementations out there, and I think I can state with almost 100% accuracy that nobody's doing what's proposed here. Exactly. They might be doing bits of it, but
So there are at least 3 or 4 implementations already doing some degree of selection. Would be really good to enforce one single set of rules.
Hi, my name is Umar from Ericsson. So I didn't see the latest update. I didn't read through. So, but we have, when we implementing, we have bunch of use cases where the conflict arised from our system teams. So I will run through definitely to see if any cases are missing here. But my one basic question is, why do we have to compare mapping server prefix and the actual prefix advertisement? Because these two are different kind of, though they're reflecting the same thing, but the comparison point probably is too much between the mapping server prefixes, and because some implementations may not do mapping server at all.
yeah. So a couple comments there. When you say some implementations don't do mapping server at all, that may well be true. But if you have a deployment and you want to get consistent conflict resolution, then if you're going to use a mapping server, everybody has to use it and support it, or nobody has to use it. You can't go halfway.
Wim Hendricks, Nokia. Thanks for doing this work, right? So I think we believe that the quarantining is actually our preferred method of resolving the conflict, if possible, because I think it gives us the implementation can remain very simple, but actually get the benefit of what we try to achieve. But again, thanks for doing the work, because it's important.
On the other hand, Orange. So thanks for having driven the consensus on SRG conflict. Thank you. I have a clarification question on slide 7. So why do you say it's easier to diagnose in one case compared to the other? A priori, in both cases, we have the same entries in conflict. In both cases, the node will notify the service provider for those conflicts, and then it's about the service provider to resolve the conflict. Why is it easier to diagnose in one case?
So the response that I really want to give you is, we don't have to agree on this. We don't have to agree on this.
Okay.
Okay, this was my personal evaluation. I think what we have to agree on is the conflict resolution policy.
Sure, but I was asking why did you say it's easier to diagnose?
Well, simply because all of the traffic that's affected by the conflict is going to get dropped. So you're going to notice it right away.
So it's easier to detect, which
Yes,
is a bit
it's
different.
detection. I understand the argument, and you've made it pretty eloquently. that this may not be the desirable outcome. And I think that's what we're trying to address with the revisions to the preference rule. But as far as detecting, yeah, you'll notice it right away.
I disagree. You don't need to drop 10 gig of traffic to detect a problem. Dropping 1 gig of traffic or dropping 1 PE or 2 PE, usually enough to raise alarms.
Okay.
Because the bigger the problem you make, the more pressure you put to operational people, and they will be asked to find a solution very quickly, and sometimes it's before the diagnostic is done, and it's not the good reaction. So, not sure putting more pressure on people will easier to diagnose and correct.
Okay, point taken.
So actually, we decided to do so listening to you and Stefan, where you didn't want to drop all the traffic, so to discard all the prefixes that have potential overlap. So hence we decided to remove, so if you go to the slide with comparison, we're only removing the 333, while 111 and 222 are still being forwarded because there's a way to do so. It has the less operational impact on you.
Yeah, exactly. I mean, to me, this is the key slide. What is it? These two slides, the preference rule. Let's agree on the preference rule. Let's agree on the policy we apply. That wasn't me, right? Oh, did I? I didn't know I had that power. On the policy that we apply using the preference rule. That to me is the key element. And as a matter of, my opinion, I would like to see us use the quarantine. I think it accomplishes the goals with the preference rule we've defined of minimizing the traffic that will be dropped when you have a conflict, because it takes the larger ranges and it chooses to ignore them, but it also makes the implementation relatively straightforward and easier to debug. If you start breaking these pieces, if you use the overlap only, I think you're going to end up with a much more complex implementation, more likelihood of inconsistent behavior, more likelihood of bugs.
So punching holes, creating all the state to keep holes will make the solution absolutely impossible to operate.
Shraddha Hegde, Juniper Networks. I think the policy preference rules, making the range as the first preference is a welcome change. I haven't thought about the other rules, what order should be, but having range at the top makes sense. And as far as the policy for handling the conflict goes, I think overlap should be the one which gives maximum advantage for the operators and network administrators for network upgrades and such. So probably, I think that should be the preferred one.
It's Wyndham Cisco Systems. I'd agree with Les that the quarantine is a much more straightforward, and you got to look at this. I mean, the functionality here, we're handling an error case. We don't want to put all sorts of complexity in it. I remember there was a functional case for this for cooperation between OSPF AVRs to automatically try and figure out the longest range that could be summarized, so you didn't have to configure any ranges. And as you added AVRs and things, it got messier and messier. So I would highly prefer quarantine to trying to figure out where the conflicts are and generate little pieces like that.
John Hardwick, Metaswitch. I'd also highly prefer the quarantine. And I think the overlap only thing looks, we have a fairly simple example here and it already looks quite complex, but it could be a lot worse than this in general. And you don't want to over-design your error handling generally. So I would rather go with the quarantine.
Grand Orange. So I agree it's improved compared to V0. I will need to see the draft and the text to have a real opinion. about the algorithm, because it's a good overview, but devil is in the detail, and so I need time to get into this. But indeed, it's better to give preference to prefix seed, and you that reflected with smaller range wins. So in slide 13, even with quarantine, you can black hole we have 50 PE. But the good news, it's 50 PE which are not SR capable yet. The more the more deployment of SR, the less impact on the network. So it's much better. But still, I need to read the draft. So V1, which is to be published, to give a real feedback. Definitely, it's a right direction.
Thank you.
John Scudder, Juniper Networks. I'm not going to walk up to the mic, but Bruno, don't sit down, because my question is partly to you. So I'm mostly sympathetic to the quarantine is simpler, so we should pick that one argument. The only question in my mind, and I don't actually run one of these networks, so I don't have a good sense of this, is in other places where we have similar problems, where we have implementers who say, I want to do the simplest possible error handling as long as it's predictable. It's fine. Just pick the simplest thing. So because of who I am, I'm thinking about BGP, and we did that for 20 years. And then we eventually had operators beat us around the head and shoulders and make us do something more complicated. And the reason was because the error cases were not as exceptional as we thought they were. If we have some, good reason to think that this error case may not be very exceptional, then I kind of agree that maybe we should think about the overlap only thing. But if we don't have, if we really believe that it is a very exceptional case to ever see this, and we don't really expect to see it in the field, then let's not make our lives harder than we have to. So that is my opinion with no chair's hat on.
If you ask me my preference as network operator, clearly I prefer the less impact on network, which would be only dropping the seed, which are clearly in conflict, and keeping all the seed which are not in conflict. So we are not going to discuss the complexity based on the slides. That's why I say I'll discuss based on the draft,
Yeah.
the mailing list. Regarding how exceptional is it? It could be based on a CLI error. So one person doing a CLI error, easy to do so. We had some CLI in the past where some people have redistributed the full routing into ISIS because the CLI was not intuitive or people made a mistake. So I think it's really possible that someone write a bad mapping server entry. I don't think it would be exceptional. So clearly, I would prefer to only drop the seed in conflict, but I have to look at the draft for more details, evaluate complexity of the algorithm. A priori, I would say that you may not have a need to create overlap, fake overlap entries. Maybe you can, for each seed or each prefix, you can ask what is the best mapping. Without having to create fake entries in your database. I need to think more about it.
Yes,
I understand that the yellow ones you are creating this. You are creating the yellow entries in your local database, or
So this is not specifying an implementation.
yes. So
It's a conceptual. I mean, how you actually store this in your database and how you choose to break up the advertised entry into the requisite pieces is an implementation issue. But conceptually, you're going to have to end up with this functionality. whatever the entries in your database look like.
Conceptually, you're looking for a seed for a given prefix. So you're looking for the best match. You have all the matches, and you take the best one. You may not need to create the yellow fake entries, but we have to discuss on the mailing list. But in all cases, it's an improvement. So
I know. It's kind of a statement. AC Lindum. I think in this case, there's been a couple analogies made to redistribution and to BGP error handling. And I think those are really different cases. I mean, I don't think you can make this analogy to this. Because in this case, really, would you ever have a mapping server that was in a different administrative domain? I don't think we've come up with that use case where the mapping servers in a different administrative domain. And here, on a single mapping server, there's this is explicit. This isn't like redistribution where you don't specify everything. This is explicit. There's no reason why the configuration for a single mapping server should ever accept a conflict. I mean, I could write this code this afternoon, and a single one. So the only time you could ever have this problem, if you have two mapping servers with disjoint configurations. So the only place where it would be an error by configuring the two mapping servers. But again, they are also under a single administrative domain. So there could be higher level, like orchestration, in the policy server, checking there to make sure that they were configured identically, because you'd never really want to have mapping servers with different configurations. For at least for this part, for the part of the mapping. So I don't really see the chance of error being that big.
Nothing can go wrong.
No, Orange again. I think you can have errors. First, mapping servers, you need two for redundancy. So if you have two mapping servers, you have two advertisements. If you change the configuration on one, it may conflict with the other. And then you can have conflict between the mapping server and the prefix seed, each segment routing node. So I think error can happen. Second, I think the comparison with BGP error handling is a good one. The point is that error may happen, and I don't think the reaction. I don't think the point of view, which is my implementation is good. It will never make an error, and if I find an error, it's the bad implementation. It should not be there. I don't think so. Error happen. And first, when you see an error, and second, when you see an error, you believe it's the sender's fault. Actually, it could be your fault. It could be the reception which is in fault. And so you believe maybe the sender is just too buggy to send a message, but actually it's a receiver which misunderstood something. So I think errors happens definitely on the service provider side, but also on the vendor side. So errors happen, and we need to design something which is robust to error, because they will happen, even within a single administrative domain.
And we're closing the line after Shraddha.
Representing co-authors of segment routing Young model, we are closely following this work, and the intention is to have immediate comparison between intended state and state as is, so an error would be immediately visible before actually deploying it. So at the moment we agree what it is, it will be visible in the model as well, so we'll be able to figure out there's something wrong in configuration before it actually happens. And yes, error should happen.
So I have a comment on the mapping server configuration and the possibility of having a conflict. So to me, it looks like it's pretty common, because if you think you have a 200 node network and 100 nodes having SR and 100 other nodes which do not have SR, and you just want to configure a range, prefix 1 to 100, SID is 1 to 100. But all these IP addresses in this range may not be, consecutively in this part of the 100 nodes. One such node could be lying on the other side. So, so to me, if you have a policy which where you do overlap only, then it's possible you just, an administrator just configures prefix 1 to 100, a range, mapping range, 1 to 100 and assigns a SID 1 to 100, and whoever makes if a certain prefix in that range defines its own SID, a different SID, which doesn't fall under that range, and if that is given a more priority, like what we said, the smaller range wins, right? So the actual prefix SID advertisement is going to win over the range. So so if that is the case, then I think the administrator need not have to worry about finding out which prefix lies in which side of the network and such. So to me, it looks very common and it makes things simpler.
So just one point of clarification here. The fact that you have the same prefix SID pair advertised in two advertisements with different ranges is not the definition of a conflict. Just to be clear. Okay, a conflict occurs because we end up with different SIDs assigned to the same prefix or the same SID assigned to different prefixes.
So the
Okay,
example that I'm giving is the different SID assigned to the same prefix. One comes as part of mapping advertisement in the mapping range, and the other comes as a prefix SID advertisement.
okay. My point, the point I'm just trying to emphasize here is once you have a conflict, the question now arises, are the rest of the, how did the conflict occur? Did the conflict occur because the range was fine, but the starting SID was the wrong starting SID? In which case, every SID assignment in that range is potentially the wrong assignment. You have no way of knowing. And you and I could sit down and come up with examples where one strategy works much better, and then another example where the other strategy works much better. We're never going to win that way. We're going to have to make a choice, and sometimes the choice we make will be optimal, and sometimes it won't.
Yeah, sure.
Any last words? Yeah, it's handy, isn't it? What? So, right, Stefano pointed out that,
So just I had put on the last slide, we do want to get this adopted. I think it's fair to say what we want to adopt is V1 of the draft, which doesn't mean it's the last version. And V1 of the draft will include the essence of what I presented here, which V0 does not. Now, to me, working group adoption doesn't mean we're done talking about, the preference rule or the strategy. To me, it means we've all agreed this is important work. We want to take it, and we want to take it to resolution.
Yep, I agree with all those things you just said, and make it quick.
So when you put out V1 of the draft, it would be good to actually leave that as an open option so that at working group adoption, there is basically, it's clear that that still has to be decided by the working group.
Point taken.
One question, when do you think you can send the V1 version? Okay, so maybe we can wait 1 week?
Yeah. We'll
Okay.
wait for the new rev and then do the adoption thing.
Cool.
Thank you.
Okay, I want to talk about computed multicast for Spring, in particular MPLS-based Spring. This draft's co-authored with Jeff. I'll state up front, could this technique also be applied to V6? I suspect it actually can, just not invested the cycles to completely bottom that out. So what the draft does, it describes a method of multicast tree construction where we simplify it down to only having to install state in the nodes that have an explicit role in the multicast tree, which means either they're going to be sending traffic into the tree as a root, going to be syncing traffic as a leaf, or they're explicitly going to be replicating traffic. And then what we do is we take advantage of the a priori set of unicast tunnels in Spring to interconnect those points in the network. So what the draft actually describes is, well, there's a bit of terminology we need to introduce to make this consistent, goes through the overall approach, describes how we can do both loose or specified multicast trees to sort of any degree of granularity, describes the necessary algorithms and the fib installation procedures. Now, in order to do this, the individual nodes computing the multicast tree need comprehensive knowledge. And what that means is they need to understand both topology and they need to understand which nodes are participating in which multicast trees. So to make sure all the nodes have this information, what we do is we add some TLVs into the routing protocol to advertise multicast membership. This was done before in MOSPF, done more recently in shortest path bridging, RFC 6329. So, I mean, it's fairly well understood, and there's exemplars of this particular approach actually being deployed and working. Now, when we combine it with the tunneling, the hybrid construction approach where we use unicast tunneling, we get a whole lot of benefits. Well, first off, the fact that the multicast registrations are in the IGP means we already had a minimum amount of messaging to converge the network on a topology change, because it's only the topology change messages that are necessary for all nodes to have complete information. We've dramatically reduced the data plane state because we're using unicast tunnels. To give an example of this, if I had a multicast tree that had a root and 5 leaves, the absolute worst case would be that 10 nodes needed to install state to fully implement that tree, irrespective of the tree topology or the network size. Turns out that the requirements for tree construction means we're actually going to produce trees that have minimized bandwidth requirements. These are going to be either minimum cost or near minimum cost trees. And in an example representative network, that's going to save about 30% of bandwidth compared to the way trees are constructed now. We're looking at unicast recovery for most failures because of this sparse state and unicast tunnel construction technique. We're reusing the existing MPLS data plane, and there's this serendipitous component to this, and that is the fact that we're using tunnels. Most nodes are going to realize for a given multicast tree, they don't need to see it through to completion, and that dramatically reduces the computation requirements and makes this actually a tractable approach. So it is a bit complicated and requires some sophistication. The fact that we are using tunnels with ECMP means there are fairly strict requirements on the tunnel construction to make sure we do not have duplicate packets on any given interface. Because if I'm sending a packet on interface A, B, and C, and a packet on D, E, and F, I could potentially have a conflict if, when I resolve those, were ECMP, where there's an overlapping set of packets. What this actually requires is that we construct pretty much minimum cost, like I said, or near minimum cost trees. So this is one of these serendipitous things where the requirements of tree construction actually drive an advantage. This also means, though, that we are computing a unique solution per individual multicast tree. So this does start to get computationally expensive. Now, to do this, there's a tree pruning algorithm. It's described in the draft. And what we do is we compute the shortest path tree from any given root, and then we proceed to apply a series of prunes to it. Now, there's 2 classes of prunes. The first is the comparatively simple and obvious, and if we apply those prunes repeatedly to the shortest path tree, and we end up fully resolving the tree, and what I mean by fully resolving the tree is that every leaf has a unique shortest path to the root after I factored out multipath, that will actually resolve about 97% of the leaves. And we can actually declare that tree safe, minimum cost, and move on. If we do not completely resolve the tree using those roots, we move into a second class of pruning, which I would describe as best guesses. And what that means is that when we're done and we fully resolved the tree, we need to do a quick audit to make sure that tree is ECMP friendly. Now, it turns out best guesses are actually pretty good. And it's only a very tiny fraction of those leaves that were not resolved that that will require a fix. And what that usually means is we're going to move their attachment point to a node that's closer to them. Yes, this is computationally expensive. But the fact that we're using tunnels means most nodes are not going to install state for a given multicast distribution tree. They can figure out fairly early in computing that tree that they can opt out. They're not going to need to do anything. And there's the second benefit to this is that, at least in my experience, synchronizing the forwarding database with the control plane was a significant part of convergence. And if I actually minimize the amount of state that needs to be synchronized between the control plane and the forwarding plane, that buys me some extra time in terms of my overall budget to converge the network. Now, this is a bit more than a purely academic exercise. Having had this approach, realized it was going to be intense from the computation point of view, went out and wrote some code to go, okay, first off, we wanted to validate that this actually, the algorithm was correct. And we also wanted to get a sense of how tractable it was. Now, these are, shall we say, representative numbers. They were run on a laptop, 1.8 gig i5 to be precise, single-threaded. And after talking to product managers, they said, well, you got to do this on a 1,000-node network or nobody's going to take you seriously. Net result being that, at least for the code that we've got, reasonably optimized. I used to think I wrote reasonably shit-out code in my youth. We were cranking about resolving 1.2 million endpoints per second in a 1,000-node network. And I guess the key point here is that this is one of those things that Moore's Law is only going to be kind to, because the networks aren't growing exponentially, but compute power is continuing to grow exponentially. Now, so far what I've described is the notion of a completely loose multicast tree, where what I've done is I've advertised only the roots and the leaves, and the IGP filled in the gaps to produce a minimum cost tree constructed of unicast tunnels and replication points in the middle. If we want to do a strict tree, we simply need to concatenate a bunch of loose trees. Now what we do is we give each one its own segment identifier, and we do this for very specific, and we cross-connect those segment identifiers at the waypoints. Now, we do this for a very specific reason. A completely loose tree can be guaranteed to be loop-free. A completely strict tree can be guaranteed to be loop-free. A tree that combines those things cannot guarantee to be completely loop-free and planar at all points or across all topologies. So if each loop-free component has a unique SID, if there is a conflict between the computed parts and the pin parts, the fact that they have different SIDs means there is not a conflict and we don't end up with any sort of forwarding loops in it. So very simply, how do we do this? We advertise in the IGP simply the list of the waypoints and the SID cross connects that fully describe that particular tree, and we can specify a multicast tree to pretty much any degree of granularity in terms of how strict or how loose it actually is. So that's a very quick overview of the technology that's in the draft. We've published the framework. We got a couple of future drafts to bring forward that would describe the required IGP extensions, and they're actually really trivial. Exemplars exist in, like I said, RFC 6329. We've also done some work on interworking with existing mechanisms. Our intention is to pursue standards track. There is some discussion as to whether it's going to be here or in PIM or whatever. I'll actually let the management sort that out. I'm simply telling you where we want to go with this. And so that being said, are there any questions?
Yeah. This is Greg, Cisco. Is there a particular multicast problem you're trying to solve with this?
Sorry, could you say that again?
Is there a particular challenge with multicast current solutions that you're trying to improve or solve with this solution?
There isn't a particular class of multicast problems I'm looking to solve, but I'm just looking to improve multicast in general.
And how does this improve it?
Because it produces minimum cost trees that require a minimum amount of state to implement.
Minimum's hard to define because the state's still there. I'm trying to compare this to solutions we already have that are topology only driven, where we don't have any flow state any longer. I mean, minimizing where the flow state has to be doesn't minimize the challenges of maintaining that flow state that's there. I'm thinking of deployments we've got tens of thousands of entries.
Yeah, I have to admit, I'm sorry you're breaking up from here because the speakers are all pointing away from me. So all I'm getting is primarily echo. So I didn't fully get your comment.
You're not removing
the mic in the front.
Pardon? Oh, mic in the front, sure.
My wife tells me I'm deaf. I seem to be proving it.
So I step back and just having dealt with multi-deployments, the challenge is the flow state itself, the fact that it's there anyway. Minimizing where we have it doesn't get rid of it. It just kind of focuses where the problems are, but it's still a problem. Those particular deployments, when they're having tens of thousands of entries, recomputing at all is the challenge. Where that recomputation takes place doesn't seem to be the problem. So I'm wondering if we're actually trying to look at a multicast and the challenges that we have in multicast and finding a way where we can resolve that, or we're just trying to take the multicast semantics and shove it into Spring.
I'm not necessarily trying to shove it into Spring. I worked on shortest path bridging and was actually a big fan of the computed approach, but one of the consequences of that was that it did produce a lot of state. It produced really cool efficiency because I would do a full mesh of shortest path trees. But when the suggestion was made, well, what about applying that to Spring? It was sort of realized, well, you know, Spring has some unique features that we can take advantage of to actually make it work even better. And so from my point of view, taking multicast, reducing the bandwidth requirements, reducing the amount of state, et cetera, and this was going to be computationally intensive, but the fact that because most nodes did not have to run the completion for every tree, we could reduce the amount of computation. There seemed to be a lot of serendipitous efficiency that could be found in this.
Well, you made a claim there of reducing bandwidth requirements, so I'm kind of confused what that would be. I mean, using network-based replication reduces bandwidth requirements in itself. Moving where those replication points doesn't change that in any way. So if we just move that off the table and just look at the computation challenges of maintaining state at all, it seems like if we're trying to do this ingress defined, that means ingress defined, packet defined, nothing inside the network, no flow state inside the network that would actually meet the model we have with unicast seems to be a better design goal rather than just trying to take the semantics of trees and sticking that into segments.
Okay, so are you referring to beer when you mentioned the ingress?
Sure, let's talk about beer.
Yeah, okay. From my point of view, the efficiency of bandwidth in any individual packet put into a beer multicast tree depends on the entropy source. Because at every node, at least if you're doing ECMP, it has to pull the bitmap apart, individually resolve which outgoing interface it's going to use for each bit, then proceed to recombine it, sort out where the conflicts are, and forward the packet on.
Just talking about replication. Replication is a requirement if you're doing any sort of replication in the node. How it does the lookup to define those replication points is relevant.
Mm-hmm.
We got forwarding mechanisms already that are parallelized or serialized, and we haven't had any conflict at all with any of the silicon vendors around that. The challenges really come down to replicating itself. However you do the lookup, however you define that replication, you got to replicate that packet across the switch fabric and out the egress interface.
Right, but in terms of the actual number of the number of hops taken to fully distribute one copy of a packet to all receivers, to me, is the measure of efficiency. And in this case, I'm using minimum cost trees where it's the fewest number of hops in the network to do that.
Do that with a subdomain.
Pardon?
Do that with a subdomain. You're taking a very particular topological requirement or a topological corner case and using that as the objective. Because not all topologies will have that case where that's the efficiency. If you look about what replication provides in the first place, you talk to people and say, hey, multicast is 2% of my network traffic. Yeah, because it's multicast. I mean, they're getting the benefits of network replication from the get-go. The minimum cost trees you're trying to establish is only when you have that kind of topology where you can benefit from that. So I'm not saying it's not important. Absolutely, that would be important. But to create an entire solution under the assumption that that's a requirement seems a bit of a stretch.
Actually, okay, let me sort of reset this discussion a little bit. About a year and a half ago, for example, I tried prototyping beer because I thought it was a really cool technology. But I concluded that it was actually introducing a lot of complexity into the data plane, and compared to control plane complexity, technology trends were not going to really be that friendly to it. So where we already right now have this very simple control plane with a whole lot of operationalized tools, etc., it actually made sense to me to perhaps consider an approach where we can find it to the technology base that we had that was well understood and operationalized.
So I won't doubt your experience, absolutely. But I will provide the experience I've heard from other people that are working on other various silicon implementations. And the best way to frame that is a particular senior developer told me that in building silicon, state is expensive, logic is free. And so the data plane logic, a little bit of that added by reducing so much state was the benefit cost savings of something like beer. Because now there's no more entries than there are bits in the field or neighbors. That's it, unbounded.
Okay.
So you're presenting again.
State.
Point taken.
You're presenting again and one of the
In PIM
multi-guest
tomorrow morning.
So you guys can have this continue the conversation. And last comment from Chris, if you want to make it, and then
Sure, go for it.
Okay,
And
just,
I hope he comes to PIM.
so more on just how this actually works. For a loose tree, you would just go into a multicast distribution tree with a single label, a multicast set label, and then these combined trees, you'd use a label stack to get around this. No?
No, I can't encode a two-dimensional object in a one-dimensional label stack. So what I actually do is I have waypoints where I have to cross-connect the label, and I've advertised the waypoints in the IGP.
So perhaps in an update of the draft, a little more of like just what labels are going to go in and out.
Right. Well, we're going to sort that out with the IGP descriptions that we'll be publishing shortly. So,
thank you.
Any other questions? Okay, cool. Thank you.
Good afternoon, folks. I'm Sanjay Vardhan, presenting the 00 draft of a way to bring packet optical integration using second routing. Okay, so this is a reference topology, really, to show you the zone that we are talking about. It's got a mix of packets and optical nodes, and it's multi-layer. The applications are in the metro and the data center interconnects. And so what we wanted to do here is to expose the optical transport links in an opaque manner to the IGPs. And it's not really meant for IGP consumption, really. It is for purposes that you will see in the later slides. And then the real constraints are basically we're going to leverage the existing signaling and routing protocols, and it needs to scale for both metro and DCI scenarios. So jump into the solution itself. This is a pretty simple network we've drawn. A, B, E, and F are packet nodes. D and C are the optical nodes in the network. So if you look at from a packet network point of view, right, you've got B connected to E through a single hop, right? But what we are bringing in now is a concept of what we call a packet optical gateway. A packet optical gateway, for example, B and E are really packet optical gateways. These are
devices that have the ability to integrate both packet and optical networks. And they have the interworking function within the box itself. So what B is going to do, B and E may advertise different optical paths with different optical characteristics as transport segments, right? So you could potentially have O1, which is basically BDE. You've got O2, which is BCE. O3 is BDCE, and O4 is BCD. These optical paths are really paths that transport segments that have specific characteristics, which we intend to expose to some entity that can take further action. Okay, so when we are building, the intent is that when we are building a service from A to F, what we're doing is we are incorporating the characteristics of these transport segments into the path. So the idea is that you have a transport segment, it's an opaque abstraction of the optical plane and leaves the definition of this path to the optical domain. We're not making any attempts to integrate that. The integration is in the transport of these, carrying of these transport segments. So the basic mechanism, the underlay topology is learned using usual standard protocols. The packet optical gateway announces themselves in the IGP packet domain. That's one of the extensions to that this proposal brings in. The other thing is packet optical gateways. They announce the optical segments, the transport segments, as opaque adjacency segments into the IGP domain. The POGs, as we call them, they map the incoming labels to on the packet side to the appropriate forwarding action on the optical side, and that's left to the individual implementations. The next step is to communicate the adjacencies to a controller or a PC using BGPLS or PCPLS. That's outside the domain. And then finally, you have the controller of the PC that comes in and uses the opaque adjacency in its end-to-end path for a given service. This is pictorially showing the same thing. Step one is really announcing the prefixes, topology, label set mappings like usual. POGs basically announce themselves as along with their transport segments. They program the forwarding action, and the PC. Then number 4 is PC. Oops. I can't get this to work. All right, number 4 is to get PC, the PC communicates the prefix to label stack, which includes the new transport set labels. The changes to the existing drafts, we've just taken one example, but you would have to probably touch OSPF, BGPLS, and PCPLS too. So here we're talking of a new type of adjacency set to accommodate an opaque adjacency, and a new flag in the SR capability sub TLV to indicate the POG. There could be, this is our first rev. We're looking for feedback here. Potentially, there could be other ways of doing this too. But this is, I put in the backup slides here. So if you look at this is the extension that we're talking about. When a path is established, this is the opaque adjacency set that we generate. The type field is, again, TBD. Weight is TBD. That basically tells us what kind of optical characteristics. We've also put a domain ID. So if you go back to the picture here, all right. So here, this is the domain. So when you have a POG that comes in here and connects with this one, it actually is advertising this optical link. And this optical link basically is connecting to the remote site using this domain D1, say. This domain could be something else, and this domain could be something else. So that's what this domain ID stands for. Then we had something called opaque subtype. An opaque subtype could be an L0 or a L1. We don't know what the optical part could be, so it could potentially be a indicator signaling a L0 or an L1 optical site. The remote POG is the system ID, and then you've got the packet optical label. The packet optical label could have potentially local or global significance. And for the node, we added one more flag here, the O flag, which basically says the router is capable of performing packet optical gateway functions. Yeah, so that's pretty much what we had. This was a thought, and we thought we'd come and ask for comments and discussions.
Daniele Ceccarelli, Ericsson. I have one question. The optical, you cannot hear me?
Some echo is going on. Sorry about this.
My question is, the optical paths are pre-provisioned or provisioned on the fly?
Okay, all right, let's go back to the picture first.
Yeah,
right here.
O2.
So typically what happens is today GMPLS is pretty much running in this optical network, and if outside tool will come in here and ask this node, give me a path to one of these guys.
How that happens?
That happens to externally, completely outside the, potentially using a tool.
Planning phase?
Yes.
Not on the fly. Okay.
Exactly. And those are the ones that we want to advertise. As and when those requests come in, we advertise those. And in this draft, we were not trying to integrate any of that piece.
And those optical paths then are already provisioned, you said, but are they potential paths in the sense that I might be able to provision O1 or O2 depending on different requests, or they are already there?
They would be already there.
Yeah, thank you. AC Lindum, Cisco Systems. I just read this draft while you were presenting, so apologies that I didn't read
No
before.
issues.
Okay, what I'm wondering is I looked at it, I looked at the encodings, and I'm wondering what information are in those that the PCE controller is going to use above and beyond the normal adjacency in the opaque adjacency. It doesn't seem like there's anything the PCE that I can see that it could use. I think you need to clarify
Sure.
what advantage.
So when you're looking at an optical link, there are very different characteristics. You could potentially be talking about latency, you could be talking bandwidth, you could be talking protection or restoration. These are characteristics of the link itself. So those basically are the ones that the PC is calculating.
That's true, but they're not in the encodings you have today. You just have a regular, just like it looks like an adjacency, similar. Would there be some correlator that correlates the GMPLS and the?
That is outside the scope of this this draft, but absolutely there's potential for that.
Wim Hendricks, Nokia. I had a similar question along the same line. Is there is a binding TLV already in segment routing? So have you looked at leveraging that to?
Sorry, can you repeat it again?
There is a binding TLV, which is actually making a label mapping to an RSVP, TLSP, or LDP, or whatever, and you could actually leverage this also for GMPLS.
Sure, absolutely.
And I think it sounds to me like a better framework to start from, because then you can leverage all the extensions from PCE and all of that, because that's all being worked on already.
Sure, we can take a look at that.
Yeah.
Hi, Stefano. I think the idea is useful because what you're addressing here, it's a topology distribution thing. I mean, you want to distribute something more about your ASIS adjacency. Now, this is not new. We already tried to address this in multiple cases, and the last one, I think, is a draft in the ASIS working group called Layer 2 bundles, where for a single ASIS adjacency, you describe what is the real connectivity you have underneath that adjacency. And this looks very similar. I'm not saying that it's the same, but it's similar. But I think it's a good idea because we need more information about layer 3 adjacencies. Using the binding SID, yeah, maybe, but that's not exactly the same thing. Here, you really want to know what happens between two adjacent boxes that have an IGP adjacency. So I think it makes sense to me to extend the IGP. The thing you should look at is what already is being worked out in the various protocol working groups, because thinking about the layer 2 bundles draft, I think you could leverage that and maybe think about an extension to that and fit your optical information.
Sure, thank you.
So to extend on Wim comments we discussed this before, I think binding TLV is more suitable mechanism to distribute this information because it's only relevant to what you call gateway, not which have both packet and optical connectivity. And binding TLV has been defined to provide, to inject information external to the packet domain, which is exactly what you're trying to do.
Yes.
Hi, Igor Briskin, Huawei. My question is that the optical path, right? So it potentially can support IP link, right, in the IP topology.
These are not IP links. So that was the whole idea behind it, is to not include it as an IP link. You could potentially do that by having them as individual interfaces that connect between A and B, between the two POGs. The idea here was to keep the same same topology from an from a IGP perspective, but at the same time expose it to the optical domain so that the optical domain can actually give feedback back for the end-to-end path.
So in TS working group, we actually call it as a non-committed link, right? So basically, it would be possible to actually set up the optical path and declare that IP link, right? So the fact that it's not actually committed or advertised, it's I don't think it brings like a lot of novelty into the discussion. I don't understand.
Yeah. So again, this is not a unique problem that we're solving. It's just another way of bringing segment routing into packet optical integration.
AC Lindemann, I think it kind of clicked for me now, and I think what's needed is a discussion of the correlation of the entry and exit point to the optical network, and just kind of conceptually, you don't think so, Stefano? You know, and whether you do it with a binding SID or whatever, that because what's inside the opaque link is a whole optical topology, and you're not using segment routing for that, at least not today. You're using GMPLS.
At the moment, because that's what you're doing, but
exactly,
yeah,
exactly, yeah.
right.
I mean, it wouldn't be opaque if you were using segment routing within
exactly
the GMPLS domain. You wouldn't need this opaque adjacency.
So one additional comment, Igor Briskin. So basically, the path, optical path, you have to also consider the adaptation capabilities, right? Whether you can actually use it as a link when it have to be used as a link, as IP link, right? So basically, it's not just optical path that could be set up from A to B. It also has to have certain adaptation capabilities to adopt IP layer traffic.
Right.
To repeat my comment that I made to AC, I think if I understood correctly, is that the only thing you want to do here is to really give the optical characteristic of an ISIS adjacency.
You don't want to propagate the whole topology of your topology layer. Is that correct?
Yeah, that is correct.
Okay.
That is correct. The idea is to have an end-to-end story for the whole thing, so that when you're actually programming the head end, you're including the optical segments, the transport segments as part of your segment list.
And so, yeah, okay, so that was my understanding too. So it looks obvious to me that you would need to multiple adjacency seed per ISIS adjacency, one for each optical path that sits underneath that specific adjacency.
That is a correct statement.
Now, ISIS, segment routing extension, as well as OSPF, allows already to have multiple adjacency sets allocated to a routing protocol adjacency. So the missing information here is just those optical attributes that will tell the PCE how to compute and which one to prefer.
So the only thing what we wanted to avoid is increasing the number of links in the topology. If you increase the number of links in the topology, your path computations change, those characteristics change. That is the idea behind this. Basically what we wanted to do was to encapsulate all that.
Yeah.
And I'd like to close the line after the people who are standing up right now. So you can do your comment if you want, Rajiv, but keep it short.
Hi, this is Dhruv. So in PC, we also have interlayer model. There can be PC in the optical layer, which can interact with the PC, which is handling the SR. So we need to also talk about other interlayer models for use of PC already there. Currently, in the draft.
Yes, you're absolutely correct. I think that'll be the second order once we go past this discussion.
But do you really see a use where currently you have a PC only in the SR, and for the optical domain you have nothing? So
another PC, correct? And we haven't, at least in this draft, we're not trying to integrate any of that.
But in that case, it's better to use the PCEP mechanisms which are already in place rather than advertising things in IGP. And you can use interlayer path computation and figure out the SID binding and other things rather than propagating the whole thing in IGP.
That is correct. The only thing is the optical link characteristics, the PCE needs to get that somehow, right? And that is the reason why we are propagating this.
So,
and we have PCEP for that.
okay, AC Lindum again. I think, yeah, you just need to discuss, do you expect the PCE computation to include the characteristics of the optical network, and this to only identify the endpoints, the gateways, and it's truly
potentially at some point.
Yeah, I think you need a little discussion of that.
Sure.
Rajiv Asari, Cisco. I'm scratching my head on the need for having this information in the routing, ISIS or OSPF to begin with. So am I correct to understand that it's really intended for some device in the network to propagate that to the PCE or the controller?
That is a correct statement.
Is that it?
That's one of the reasons. That is correct.
What's the other reason?
The other reason is if you have these as optical links, you would basically, what you're doing is your adjacency that you're advertising is not, it's not a regular IGP adjacency. Hence, it is not part of your IGP path calculations. And what you're also doing, the head end that gets the segment list can take a look at Oh, you're doing that. Okay, I was wondering if you're not. All right. So what the head end could do is look at the domain IDs of the segments that are part of the segment list and take some other decisions, other policies that we are not really describing in this draft.
But I guess where I'm going with this is the head end would be told about the segment list and the labels.
Correct.
By the controller anyway.
Yes.
So it doesn't really need to know that from ISIS or OSPF standpoint, there's really no usage or benefit for the head end to know what all optical adjacencies exist in every part of my network between a pair of
No,
routers.
so that is the policy part of it, right? If you really want that to be part of that, that's the reason we distributed it for future use, potential future use.
Okay,
I'm still scratching, but
yeah,
I'll
I'm
put
gonna
that
we
on
can
the
talk
list.
about this.
I'm going to
Thank
cut
you.
it off. We're out of time. Thank you very much.
Thank you. Thank you.
Good afternoon. I'm Shraddha Agade, talking about the node protection for SRT parts on behalf of the co-authors of the draft. So the topics for today is why do we need node protection at all? Let's see a bit about how explicit paths are defined in segment routing and why something special needs to be done for node protection for these explicit paths. And we'll look at a solution that we are proposing in this draft. So, so node protection is very much essential because service providers have to. So service providers have to give service SLAs for the services. So high network resiliency is very much needed. So having a FRR protection for the routes is very much essential to achieve the sub-second convergence. So nodes can go out of service because of software crashes or some catastrophic events or power failure. So it's very important to have the node protection and have the FRR paths that provide node protection. So in SR, the explicit paths could be made using a set of adjacency sits or a set of node sits or a combination of these two, that combination of adjacency and node sits, or a list of binding sits and adjacency sits. So the difference in SR is that the midpoints do not maintain any state. So if you have a adjacency sit programmed in your forwarding plane, you don't know what paths would be using it. There could be two different ingresses which could be sending traffic over that particular link, and that might be using that particular label and going to two different destinations. So there's no way to figure out which is the next hop, so that if the node, the next node goes down, I mean where to forward the traffic to. As opposed to RSVP LSPs, where the LSPs do maintain midpoint state, so you know that LSP corresponds to which particular path, so you know where the next hop is. So it's easy to build a bypass LSP, but that's not the case in case of SR. So some special mechanisms are required to provide node protection. So basically, the PLR needs to figure out the next label in the label stack to find out where exactly the traffic is headed to, and then provide protection for the traffic. So this is explaining how the explicit paths are built using node sets, and what exactly is the problem with the explicit paths using node sets. So when you build a stack of labels using node sets, it's possible that one of those nodes which define that particular node set, that goes down. So in that case, without looking at the next label in the stack, it's not possible to figure out what has to be done with the traffic. So usually LFA mechanisms, what they do is if your destination is your failure node, then it just drops the traffic and does not provide any protection. So in case of SR, it's essential that you look into the bottom label, the next label in the label stack, and then forward the traffic. So this is an example where there is an explicit path built from R1 to R5. So R1 to R2 to R3, R4, R5 is the SPF path, and the explicit path is built using two. So the explicit path that we need is R1 to R7 to R8 to R4 to R5, and this path can be built using two node sets, as shown on the left side. A two label stack. Top label is 1008, which takes you to the R8, and then next label is 3005, which takes you from R8 to R5. So the SRGBs and the SIDs for these nodes are as described in the figure. So let's take a case of different SRGBs for different nodes. I mean, this is a practical problem. Maybe it's not possible to have same SRGB across all nodes. So in that case, let's take a case where R8 has a different SRGB. So when R8 goes down, so R7 is looking, trying to forward a packet which is having these two labels, 3005 and 1008. And it needs to understand the label 3005 to be able to forward the traffic to R5. So when R7 has to understand the label 3005 from the perspective of the failed node, which is R8. So the way this can be solved is by building the context tables. So it's like R7 is the PLR, so it builds context tables for all its neighbors. So the context table consists of the labels which correspond to the failure node. So the failure node has the sRGB 3000 to 4000. So the context table of R8, which R7 builds, has those labels in its table, and then it builds the actions for those labels based on its own SPF and backup SPF computations. So R7's SPF computation. Let's take the example of the label 3005. So for node 5, R7 has computed SPF paths and backup SPF paths. So SPF path is via R7 to R1 to R2, R3, R4, and R5. And backup SPF is via R7 to R8 to R4 to R5. So among these two, it chooses the path which avoids the failure node, which is R8, and then puts this information in the context table of R8. So we have in the context table of R8, we have 3005. It swaps with 1005 and then forwards it to R1. So what happens is basically when R7 to R8 adjacency comes up, R7 builds a context table for R8 for all the labels, that is all the node sets which R8 corresponds to, corresponding to the R8's sRGB. So similarly, for a path which is built using adjacency sets, also needs the context table. So in this example, an explicit path from R1 to R5 is needed from, explicit path is going from R1 to R2 to R3 to R8, R4, and R5, and and the entire path is using a stack of adjacency seed labels. So if you see, top of the stack is 1034, that would take the packet from R1 to R2. The top of the stack is 1034, that would take the packet from R2 to R3, and then 1044, which would take from R3 to R8, and so on. So when R8 goes down, R3 cannot figure out where the packet is headed to without looking into the next label. So what R3 does is it builds the context table for R8, because R3 does not really understand the labels that are advertised by R8. So let's say R8 has advertised two labels, 1054 and 1074. So R3 need to understand these two labels and build a context table, a special table which is from R8's perspective. So the mechanism for building the context table is similar to what we have seen for node sets. So it just looks into, let's say the label 1054, it looks into for which remote end this adjacency seed is advertised for. So this adjacency seed is advertised for R4. So R3 looks into its SPF and backup SPF computations and finds out a loop-free path which avoids R8 and then programs it in the context table of R8. So if you look at the transit table at R3 for the label 1044, which is supposed to take the packet from R3 to R4, R3 to R8. So it has a pop and forward operation and programmed, and it has a backup path which says pop and look up into the context table of R8. So basically, when the packet comes, if it finds that R8 is failed, then it's supposed to pop and look up into the context table. So this slide is describing what happens on a failure. Yes. I have one more slide. So, what happens on failure is if we see at R3, we have a packet having three labels. Top of the label stack is 1044. So if R8 is down, then and the forwarding plane will be pointing to the backup next hop, which is pop and look up into the context table of R8. So the label 1044 gets popped, and then it looks up into the context table of R8. So context table of R8 has the label 1054, which is the label in the arriving packet. So it pops that the action is to pop and forward it to R4. So the packet arrives at R4 with a single label, which is 1064, and that's how the forwarding continues and FRR happens. So similar to the above two mechanisms, we can also provide protection for binding sets. So basically, binding sets they may be used to represent subpaths. So so R2 advertises a binding set for R4. So path could be any path. It could be RSVP or it could be a SR subpath. So R1 programs in its context table for label 7048, it programs the loop-free path towards R4. R4 is the remote end of this binding set. So R1 programs the context table of R2 with the label which the path which corresponds to R4. And in this case, in this example, it's using the RLFA backup path to R4. So that when a packet arrives at R1 and if R2 goes down, R1 looks into the context table of R2 and then performs the actions corresponding to the label 7048. So.
Okay, and while our next speaker comes forward, if you have any very brief comments, you can make them. Otherwise, I'll encourage you to make them on the list or after the meeting. I'm sorry, we're coming to the end of our meeting time. So, next person, please. Thank you, Shraddha.
Hi, I'm Jessica from Huawei. I will give the presentation about the tunnel segment inside SR. Because I have no much time, so I will just squeeze some to the comparison of the tunnel segment and the SP segment and the binding segment. This is a background about the segments has in the architecture have a lot of types of segments like IGB segment, BGB segment, and RSP segment. And in the architecture of the draft, it has mentioned the binding segment, and it has two scenarios. One is mapping server, another is tunnel headend. And the draft introduced a new type of segment. We call it the tunnel segment. The tunnel segment can be used to three typical use cases. One is reducing the SID stack length. One is we can span the non-SR domain. And the third is it can support different services, use multiple tunnels. And the tunnel segment can be RSVPT tunnel, SRT tunnel, or IP tunnel. The RSVPT tunnel and SRT tunnel can have the primary and secondary SPs. We skip the use cases, okay? This is the comparison of the tunnel segment and the adjacency segment. It's similar to the SP segment comparison to the adjacent segment. The first is when we use tunnel segment, the IP address is needed to be carried, and the tunnel segment can carry a lot of tunnel information, just like the SP segment. And if we use tunnel segment, it will not influence the SDB and SPF computation. This is the tunnel segment compared with SP segment. As we know that SP segment has three types of LDP segment, BGP segment, and RSVPT segment. Here we only compared to the RSVPT segment because we think the LDP and the BGP SP segment, they are fake is the prefix, but for the RSVPT SP is fake. You can understand it include the prefix and the ingress and the egress tunnel ID and the tunnel ID, 3 tuple. So now we have IGP extension and the PCP extension of the RSP segment. So we compared the two types of segments in the IGP extension and the PCP extension. When we use the tunnel segment, because the tunnel, like RSVPT tunnel, it has two SPs, like primary and secondary SPs. When the route is converted, SP or the path will change. So the SP segment has to be advertised again. But if you use the tunnel segment, it will be stable. It needn't to be advertised again. And if we use tunnel segment, we can support three types of the tunnel. And when we use tunnel segment, we have to carry the information about tunnel, like the tunnel identifier. In RSVPT, we can carry the ingress RSID, egress RSID, and tunnel ID. And besides the tunnel identifier, we can carry the tunnel attribute, like the tunnel, the bandwidth of the tunnel. It can be used to compute the SR end-to-end path. And this page explains the relationship of the tunnel segment and the binding segment. We can, because the binding segment in IGP extension, it uses the binding TLV. But in the PCEP segment now, there is a new theory about the binding, label binding. So we can only extend the IGP binding theory to include the new type of segment. And for the PCEP, we extend to carry the tunnel-related objects or theory. This we have the another drafter in the PCE working group. This is a requirement of the control plane about it includes the IGP extensions, BGP extensions, and the PCP extensions. Now we have proposed some drafts about the PCP extensions, and for the IGP extension, we didn't propose the draft now. Any questions?
Questions or comments? Thank you very much.
Thank you.
And we are done. Thank you, everybody. And we'll see you next time. And I know it was a long time ago that we talked about making progress on the first few documents, but we need to make progress on them before the next meeting, and that will mean everyone's attention on the mailing lists and during working group last calls, please. Thank you. Also, if you have a blue sheet, if you would not mind bringing it forward, that would be great.
Setup here in terms of, because I'm amazed that it actually propagates to the VDEC screen as well. VDEC goes funny.